move ahead with the topic frequency response of frequency response of continuous time LTI system. A LTI system I am drawing here, some input is applied on it and we got some result, excitation and response. If applied input is impulse, result is impulse response. We took Fourier transform of it, result is h omega. If input is not impulse, it is general input, we take Fourier transform, result is xt convolution ht. If Fourier transform, y omega equals to h omega x omega. Result come from convolution between xt and ht, and in Fourier frequency domain it come from multiplication between these two Fourier transform. Transfer function come through division of output response Fourier transform and input excitation Fourier transform. Each Fourier transform have two components, a magnitude spectra as well as phase spectra. Magnitude response and phase response. Magnitude response and phase response. Again come to y omega is magnitude response of output come from magnitude response of input multiply with magnitude response of impulse response, and phase response come from phase response of output come from phase response of input plus phase response of impulse. We add these two terms and get the result. If input is xt is e power plus j omega t, then result is, for calculating result taking Fourier transform in both direction, h omega 2 pi h omega naught multiply with impulse. That is the complete result. Y omega x omega h omega. Complete result is this. Means if by taking inverse we can conclude e power j omega naught t. It is called eigenvalue. It is called eigenfunction. For different value of t we can generate function, and eigenvalue is constant value. From this term LTI system we have some output, we can develop a expression for distortion-less transmission. For that we write a heading distortion-less transmission. What is distortion-less transmission? If for a distortion-less transmission, if exact input signal shape is reproduced at output, exact input signal shape shape is not disturbed, reproduce at output is distortionless. At output, reproduce at output is distortionless. May amplitude different and delay in time both may be exist. We can write expression for distortionless transmission is kxt minus td. Delay in time, amplitude can be modified, can be retarded 80%, 60%, 60%, 40% maybe, and some delay in the time. Delay in time produce only phase difference, linear phase difference. By taking Fourier transform of it, we get result omega td x omega. H omega e j theta h omega equals to k minus omega td. H omega now is k constant. Magnitude spectra is constant throughout the frequency length for distortionless transmission. And phase spectra we can denote by this also, which is linear function of omega. For definition purpose, we write amplitude of h omega is constant for entire frequency range and phase of omega is linear with frequency. For amplitude distortion we can write h omega means magnitude spectra is not constant within frequency band, means frequency component of input are transmitted with a different amount of gain or attenuation is amplitude distortion. Let's discuss with example. Some sine wave is there, 5 sine omega t. Without amplitude distortion, this waveform maintain its shape and result may be 2 sine omega t. If amplitude distortion is available here, means it does not maintain its shape. This waveform is magnified with, does not maintain its shape, magnified with different amount. Here it is 5, it is 6, it is 4, 3, 2, 0, -1, etc. Means it is not maintaining amplitude constant throughout the length, is amplitude distortion. To avoid amplitude distortion, system response in frequency domain is constant. And for phase distortion, to avoid phase distortion, it is linear with frequency, means output has different waveform than input signal because of different delay of different frequency component. If different delay provided to different frequency component, it produce phase distortion. Due to phase distortion, two terms come into picture: phase delay and group delay. It is very small topic, only formula is discussed here. We can write formula for phase delay and group delay. Phase delay may be represent TP, phase. T for phase, delay means time. Formula is phase delay formula is angle of h omega upon omega. This may be represent angle of omega upon omega. And group delay, group, G for group. Differentiation of angle of h omega upon d omega minus. This represents the group delay. This term is phase spectrum of impulse response. Impulse response. Took a phase spectrum of impulse response, first divided by a particular frequency where we want to calculate phase delay. Just with negative sign we get phase delay. For group delay we have to take first differentiation and put negative over there. We get the group delay. Phase delay and group delay. Small topic. Whenever we find impulse response Fourier transform, calculate first phase spectra and then divide by desired frequency, and in second case just differentiate and put the value of frequency. We get both the result. Different type of filter is available to us. Some Fourier analysis on it. Filtering. I discussed small topic filtering. Filtering is a process by which relative amplitude of frequency component in a signal are changed or frequency component is suppressed. Filtering is a process, it have two band, pass band and stop band. If pass band applicable, then passing of the particular frequency component omega. Stop band applicable means stopping the particular frequency band. The filtering is a process by which relative amplitude of frequency component in a signal are changed. Relative amplitude is changed. If it pass through pass band, it multiply with pass band amplitude magnitude. If pass through a stop band, it multiply with 0. All ideal filter I am discussing here, low pass filter. It exactly passes a signal set of frequency and completely reject the other. It is called low pass filter. Ideal low pass filter I already draw. Low pass filter, it is known as pass band, it is stop band. Below this frequency, all frequency is passed through this band. It is known as low pass filter. Mathematically we can represent 1 for frequency below, above which is 0. It is known as cut off frequency. Low pass filter have its bandwidth is omega L as per shown diagram. High pass filter HPF, high pass filter, H omega is 0 for a particular frequency omega H and greater than that frequency is 1. We can draw in this way omega H. Above a particular frequency it pass. In the frequency band above a particular frequency pass, it called high pass filter. No bandwidth is exist for high pass filter. band reject, ideal band pass filter, and then band reject filter we will discuss. H omega is 1 for a particular frequency range, otherwise 0. It is called band pass filter. Omega 1, omega, omega 2 and 0 here is pass for particular band, and remaining is stop band, is pass band PB, stop band SB. Bandwidth for this is omega 2 minus omega 1 as per shown in figure. Band reject filter, just reverse of it, reject particular band, zero here, omega 1, omega 2 minus omega 1 minus omega 2. Expression for this is otherwise 1. Otherwise 1. All the ideal filters are not physically realizable. All the ideal filter are not physically realizable, so we have to use practical filter for realization. All ideal filter are non-causal, or non-causal system is not physically realizable. Now we complete this topic with, it is very important topic, and we discuss the all aspect of this topic. Last point of this topic, we last topic of last question of this topic is, we we take a exam question regarding Parseval theorem. We have some spectral pattern for a signal, and we want to calculate energy of signal with Parseval theorem. As per Parseval theorem, energy of signal can be calculated without changing the domain, minus infinite infinite 1 upon 2 pi some integration minus infinite to infinite x omega mod of d omega. So we can calculate energy from this expression also, from spectrum domain diagram also. Just calculating this term, we can calculate ext minus infinite to infinite x square omega dt 2 pi x omega square d omega. By putting all the values, 1 upon 2 pi minus a to a 1 square d omega 2 pi omega minus a to a, result is a upon pi. We directly calculate energy of signal in from its spectrum via Parseval theorem. It is the example for calculating energy from